Work, energy and power. Conservation of energy. Right, the law of conservation of energy. The total energy in a system cannot be created nor destroyed, only transformed from one form to another. Now, we have a skater that is 5 meters up on a half pipe. Currently, he has a certain amount of potential energy, which is equal to the total amount of energy that he possesses at this point in time. If we allow the animation to run, we can see that the skater constantly gets back up to that 5 meter mark and is transferring his potential energy into kinetic energy and then kinetic energy back into potential. But if we put friction into the mix, the big change that's going to happen is some of that energy is going to be transferred into thermal energy. So instead of it becoming potential or kinetic and alternating between those two, some energy is wasted into thermal energy, and that means that he doesn't go as high up on the slope as he did previously. Eventually he stops moving when that thermal energy is equal to the total amount of energy, and so all energy has therefore been wasted. We also get the principle of conservation of mechanical energy. Now notice here that we have a principle and law. This can never be broken. This works in certain circumstances, but pretty much it's as good as a law. It just doesn't have as much relevance to everything as a law would have. So our principle then is, in the absence of air resistance or any external forces, which could also just be normal friction, the mechanical energy of an object is constant. And we saw that as well with the guy on the skateboard, where he kept going to the same heights each time. The equation that we use here, EP plus EK, and if we go back to what we did previously, that is mechanical energy, and that's our initial mechanical energy is always equal to our final mechanical energy. All right, example 1. We're going to look at a block falling. Right, our first example for mechanical energy. What we're going to do now is determine the velocity of the block just before it hits the ground 10 meters below its initial position. What we currently do know is that we have an initial velocity equal to 0, a final velocity, which we don't currently know at this point. We know that this thing is going to fall towards the ground at g, which is equal to 9.8 meters per second squared. And pretty much that's the information that we will need. So, because air resistance is negligible, we can use the principle of conservation of mechanical energy. This states that the initial mechanical energy will be equal to the final mechanical energy. Now, we know that mechanical energy is equal to potential energy plus kinetic energy at a point. And this will be the same for the final. Right, now we could expand this out, but there isn't really a point to do that because we know that our initial velocity is equal to 0. That means that our initial kinetic energy will therefore have to be equal to 0. And our final potential energy, the object is going to be at the ground or at 0 meters. Therefore, we know that we won't have any potential energy left over at the end. So we can then put in the values that we can use. We've got mgh, and for kinetic energy, we have half mv squared. All right, so let's substitute the values we have. We've got mass of 5 kilograms, gravity 9.8 meters per second squared, and a height of 10 meters. Then, for our final kinetic energy, we have our mass of 5, but we currently do not know that velocity. So if we calculate that, we'll get 490, and here we can have 2.5 v squared. If we solve this, we're going to have 490 divided by 2, And then we will square root that. And so the answer then, with some magical maths, is going to be 14 meters per second. Okay, now just to prove that using energy works, we can do the same thing but using kinematics. Now we know that this thing is going to accelerate down at 9.8 meters per second. It's got an initial velocity of 0. We don't know the final velocity yet. Let's pretend like we don't. And we know it's going to travel a distance of 10 meters. Therefore, we can use Vf squared is equal to Vi squared plus 2ax, or in this case, because we're using the vertical axis, we can say y. So, do the entire thing then. Our initial velocity was 0, so we can ignore that term. We've got 2 acceleration due to gravity, 9.8, and it's traveling 10 meters. Pop this into a calculator, and guarantee you we will get 14 meters per second. Now in this case, obviously doing this is actually quicker than doing the energy formula, but in the next example, we will look at something on a slope, and that's where the difference really comes in. Example 2, we're going to look at a block sliding down a slope. All right, now the next example for mechanical energy. So, in this case, we're going to determine the velocity of a block 10 meters below its initial height on a frictionless slope if we know that theta is 30 degrees. Now, if we only used energy, theta would be irrelevant, but I'm going to first show you doing kinematics and forces, and then we will look at using energy formulas. All right, so to do the kinematic method, firstly, we know that if we have a triangle here, we know that this is 10 meters. What we don't know is how long our hypotenuse is, or how long the x-axis is. So we don't know that, and we don't know that. But what we do know is that theta is equal to 30 degrees. So firstly, we can find out what r is, and that'll tell us how far this thing is going to travel from there to there. So if we take sine theta is equal to y over r, we can solve this saying sine 30 is equal to 10 over r, which means that r will be equal to 20. Okay, so we know that we're traveling 20 meters between there and there. Now, we need to find out how much force is going to push this thing down the slope due to gravity. So for that, we're going to be using Fg parallel, which is equal to mg sine theta. And so our mass of 5 kilograms, gravity 9.8 times sine 30. So this is then going to be 24.5 newtons. So we know that this object is being pushed down the slope due to gravity with 24.5 newtons. Now we can find out the acceleration that it would undergo. If we have F is equal to ma, we have a force of 24.5 newtons, a mass of 5 kilograms, and acceleration is what we're trying to calculate. And so that is going to be equal to 4.9 meters per second squared. So we have our acceleration, we have our displacement, and so we can use both of those to then find out our final velocity if we say Vf squared is equal to Vi squared plus 2ax. And so that means we will then get root. We know that our initial velocity is 0 times 2, 4.9 times the displacement of 20, and that is then going to give us a final velocity of 14 meters per second. Alright, so previously I showed you how to do this using kinematics. Now we're going to use energy concepts. Alright, this is a frictionless slope. Because of that, we know we can use the principle of conservation of mechanical energy, which tells us that the initial mechanical energy is equal to the final mechanical energy, where we have our potential plus kinetic initially, which is equal to our potential plus kinetic finally. But once again, at the top here, we have our mechanical energy, or our potential energy, which there is because it is at a height, and our kinetic energy is going to be 0 because of the things at rest initially. Then when it gets down to the bottom here, this is now a reference point, and so that means for our final potential energy, it's going to be a height of 0, therefore that whole term is just going to be equal to 0. Then we have our half mv squared, which will tell us what our velocity is at the bottom. So we substitute the values we know we've got a mass of 5 kilograms, acceleration due to gravity is 9.8, and a height of 10 meters. Plus our mass at the end, which will be 5, our velocity squared, and so that will give us 490, 2.5 v squared, and that means if we do all the maths behind it, we will eventually get to a final velocity of 14 meters per second. Okay, so you can see that this is a lot simpler than doing the kinematic equations, where if we just have an object dropping, then using kinematics is easier than using energy.